phase pipeline can lead to excessive pressure drop and hence loss in capacity. Pressure drop and gas-liquid flow is complicated by the variety of flow regimes which can exist. Current work in the Transportation Research and Engineering Department is aimed at developing better designs by better understanding of these flow regimes. This film will show these flow patterns and the effects of pipe inclination and flow rates. When gas and liquid flow together in a pipe, a variety of flow patterns can exist. For the first set of conditions we'll see, we set the liquid rate at 2 gallons per minute and the gas rate varied from 1.4 to 280 feet per second. The pipe is horizontal, 1.75 inches in diameter. At the lowest velocity, the surface is fairly smooth with small waves coming by. A bubbly plug flow occurs at a slightly higher speed. At this condition, the surface is choppy or rippled. Under these conditions, a cresting annular flow condition exists. And at this speed, most of the liquid is being transported as droplets with some liquid film at the wall. As we raise the liquid rate, the slugs or plugs that you see here are formed. It's important to know the characteristics of this flow regime because we must design the receiving facilities to be able to separate these high-speed liquid sections from their gas counterparts. Pipe slope can have a significant effect on flow pattern, especially at low rates. In the next set of runs, the liquid rate is set at 2 gallons per minute and the gas rate at 1.3 feet per second. With a minus 2 degree slope, downslope, we see a stratified wavy film with about a fourth of the pipe diameter occupied by liquid. Coming back to horizontal flow, the pipe is seen to be about half full of liquid. Changing to a plus 2 degree upslope causes a plug flow to occur of an intermittent nature. Going up to 5 degrees through 15 degrees, we see increasing amounts of backflow or recycle. This leads to an increased energy loss. This graph shows measured pressure at various gas flow rates with the test section inclined at 15 degrees and 2 gallons per minute flowing. The first data point shows the pressure that would exist with only liquid in the test section. The pressure drop is thus about 4.2 psi. With a small amount of gas injection, the flow conditions look like this. And the pressure drop has fallen to 2.2 psi. With a slightly higher gas rate, the new flow conditions are as follows. And the pressure drop continues to fall to 1.4 psi. At 3.9 feet per second, the pressure drop reaches a near minimum of 1.2 psi. And at 4.8 feet per second and beyond, pressure drop increases with further gas flow. Pressure drop in upflow is thus the sum of elevation and frictional effects. Increasing gas flow causes the elevation head to fall and the friction loss to increase. Total pressure drop then goes through a minimum, as our measurements show. If too large a pipe is used, system flow capacity may be impaired. Operation in the low velocity range also tends to be unstable. In Shell's offshore and Arctic exploration efforts, pipeline transport costs can be high, and there is a need for good design methods. Early design tools took no account of flow pattern details. Two-phase flow has proved to be fairly complicated, so that these global or macroscopic approaches are not sufficiently accurate. Better design methods must come from more realistic physical descriptions of the flow and of the way energy loss occurs.